Something is accelerating toward our sun faster than any comet ever recorded. 3I/Atlas, once thought to be a harmless interstellar visitor, is now moving at a velocity that defies orbital prediction. Each hour, its speed increases, and the closer it gets, the stranger the readings become. High-resolution solar scans reveal a growing plasma field surrounding the object, interacting directly with the sun's magnetic loops, triggering sudden flares and localized eruptions across the corona. If this connection strengthens, the effects could ripple all the way to Earth. Massive geomagnetic storms, satellite failures, even temporary blackouts. And yet NASA's recent data revisions quietly adjusted 3I/Atlas's velocity without explanation. Is this just a natural acceleration, or is something, or someone, guiding its path? Because the way it's diving toward our star doesn't look random. It looks deliberate. October 14th, 2025. Dr. Helena Marsh at the European Space Agency's Solar Orbiter Mission Control noticed something in the telemetry that made her pause mid-keystroke. Solar Orbiter had been tracking 3I/Atlas as part of a routine heliophysics observation campaign. The spacecraft's remote sensing instruments measured the comet's velocity at multiple intervals across a 72-hour period, standard procedure for determining orbital parameters. What caught Marsh's attention wasn't the velocity itself, it was the rate of change. Between October 11th and October 14th, 3I/Atlas had accelerated by 2.7 kilometers per second. That kind of velocity increase over 3 days required an explanation. Comets do accelerate as they approach the sun. Solar heating vaporizes subsurface ice, creating jets of gas that act like tiny rocket engines. This non-gravitational acceleration is well documented, but the effect typically peaks when a comet is between 2 and 3 astronomical units from the sun, where temperatures are just right for rapid ice sublimation. 3I/Atlas was currently at 1.8 astronomical units and accelerating faster than it had at 2.5 astronomical units. The pattern was inverted. Marsh ran the numbers through standard outgassing models. None matched the observed acceleration. She contacted Dr. Marco Velli at UCLA's Institute for Planets and Exoplanets, a specialist in solar wind dynamics and cometary behavior. Velli reviewed the solar orbiter data and immediately requested observations from other sources. NASA's Parker Solar Probe, closer to the sun than any human-made object, had captured magnetic field measurements during the same period. The Stereo spacecraft, positioned to view the sun from angles inaccessible to Earth-based telescopes, had imaged 3I/Atlas in extreme ultraviolet. When Velli compiled the multi-source data, a pattern emerged that had no precedent in comet research. The acceleration wasn't coming from outgassing in the traditional sense. It was electromagnetic. Parker's magnetometers showed that 3I/Atlas was surrounded by a structured magnetic field, far stronger than any previously measured around a comet. The field extended roughly 400,000 kilometers from the nucleus, creating a bubble that interacted with the solar wind. As the comet moved deeper into the sun's gravity well, this magnetic bubble was compressing, growing denser and more energetic. Velli described it as a magnetic sail, a phenomenon known to occur around magnetized planets, but never observed on a comet. The compression was generating a force that added to the gravitational acceleration, pushing 3I/Atlas toward the sun faster than gravity alone could account for. Stereo's ultraviolet images revealed the visual signature of this process. A diffuse glow surrounded 3I/Atlas, far more extensive than the typical dust and gas coma. The glow wasn't uniform, it pulsed. Every 3.8 hours, the brightness increased by approximately 15%, held for 22 minutes, then faded back to baseline. Dr. Yuki Takahashi, monitoring solar activity from Japan's Hinode Observatory, noticed something extraordinary. Each time 3I/Atlas's magnetic field pulsed, a corresponding ripple appeared in the sun's corona. Small bright points lasting a few minutes, flaring up in the region of the corona directly between the sun and the comet. The connection was unmistakable. 3I/Atlas wasn't just passively falling toward the sun, it was interacting with the solar magnetic field in real time. You're probably wondering how this is possible. The sun's magnetic field extends throughout the solar system, forming complex structures of loops, arches, and open field lines that channel the solar wind. When a magnetized object moves through this field, it can cause what's called magnetic reconnection, a violent rearrangement where field lines snap and rejoin, releasing enormous amounts of energy. This process powers solar flares and coronal mass ejections. What Takahashi observed suggested 3I/Atlas was triggering micro-reconnection events, not large enough to produce major flares, but sufficient to release localized bursts of energy in the corona. By October 28th, the reconnection events were increasing in frequency. Takahashi's log showed one event every 3.8 hours initially, matching 3I/Atlas's magnetic pulse cycle. By October 20th, the interval had shortened to 2.9 hours. By October 22nd, 2.1 hours. The pattern suggested resonance. 3I/Atlas's magnetic field was syncing with the sun's natural oscillations, and as the comet drew closer, the coupling grew stronger. Dr. Linda Vazquez, who had been tracking potential electromagnetic effects of 3I/Atlas on Earth, pulled solar wind data from NOAA's Space Weather Prediction Center. The solar wind speed measured at Earth's orbital distance had increased by 8% since October 14th. Not a massive jump, but steady and coinciding with the comet's approach. Then came the first visible proof that something unusual was happening. On October 24th, amateur astronomers across the Northern Hemisphere reported a dramatic change in 3I/Atlas's appearance. The comet's coma, previously a uniform green glow, had developed structure. Radial streamers extended from the nucleus, bright filaments that pulsed in sync with the now familiar 2.1-hour cycle. High-resolution images from the Hubble Space Telescope, obtained through a director's discretionary time request, showed these streamers in stunning detail. They weren't dust trails, they were plasma channels, ionized gas flowing along magnetic field lines that connected the comet to something. The streamers pointed toward the sun, each one perfectly aligned with the direction of the solar magnetic field at that location. Dr. Marsh compiled the observations into a preliminary report. Her conclusion was careful but clear. 3I/Atlas was generating or amplifying a magnetic field structure that actively coupled with the sun's magnetosphere. This coupling was producing measurable effects: acceleration beyond gravitational prediction, localized energy releases in the solar corona, and organized plasma flows that suggested the object was channeling energy from the solar wind. The report was submitted to ESA's Solar System Science Operations on October 25th. It was flagged for review and classified under ongoing analysis, pending verification.
October 26th. NASA's Goddard Space Flight Center issued a routine orbital update for 3I/Atlas. The revised perihelion distance now placed the object at 1.29 astronomical units from the Sun, closer than the previous estimate of 1.36 astronomical units. The update listed the change as a refinement based on improved astrometric data. No mention of the velocity anomaly, no explanation for why the approach distance had narrowed by 10 million kilometers. Dr. Vacelli noticed the update within an hour of posting. He cross-referenced it with the acceleration data from Solar Orbiter. The numbers didn't match. To reach 1.29 astronomical units at perihelion on October 29th, 3I/Atlas would need to maintain its current acceleration rate for another 3 days. But that acceleration wasn't constant. It was increasing. If the trend continued, the comet would reach perihelion even closer, possibly at 1.25 astronomical units or less. Vacelli contacted Goddard directly. His email was routed to Dr. Benjamin Torres at the Solar System Dynamics Group. Torres responded within 2 hours, unusually fast for internal NASA correspondence. The message was brief. The 1.29 astronomical unit figure represented the most probable trajectory based on weighted analysis of available observations. Alternative scenarios placing the object closer were being monitored but remained low confidence pending additional data. Torres acknowledged the non-gravitational acceleration but characterized it as within expected parameters for an active long-period comet. The email concluded with a request that Vacelli coordinate any external publications through official channels to ensure consistency in public messaging. Vacelli read between the lines. NASA knew the trajectory was uncertain. They had chosen to publish a conservative estimate rather than alarm the scientific community or public with projections showing 3I/Atlas diving deeper into the solar system than any interstellar object on record. The decision made sense from a risk management perspective. Overestimating threat or novelty could trigger unnecessary concern, but it also meant the official record didn't reflect what multiple independent data sources were showing. The comet was moving faster, approaching closer, and exhibiting electromagnetic behavior that had no natural precedent. On October 27th, the Solar Dynamics Observatory captured something that elevated concern to a new level. SDO's Atmospheric Imaging Assembly, which photographs the Sun in multiple extreme ultraviolet wavelengths, recorded a sequence of events in the corona directly along the line connecting the Sun to 3I/Atlas. At 8:14 UTC, a bright point appeared in the corona, typical of the micro-reconnection events Takahashi had been tracking. This one was different. Instead of fading after a few minutes, it intensified. Within 8 minutes, it had evolved into a small solar flare classified as C2.4 on the logarithmic scale solar physicists use. Not a major event. C-class flares are common, occurring multiple times per week during solar maximum. What made this one noteworthy was its location and timing. The flare erupted from a region of the corona with no visible sunspots, no active region designation, no prior indication of magnetic instability. Solar flares almost always originate from active regions where the Sun's magnetic field is twisted and stressed. This one appeared in a quiet area, and it appeared exactly along the magnetic connection between the Sun and 3I/Atlas. Dr. Takahashi analyzed the flare's magnetic topology using data from Hinode's Solar Optical Telescope. The field lines involved in the eruption traced back to the comet's position. Not approximately, exactly. As if something about 3I/Atlas's magnetic field had destabilized the Sun's field at that precise point.
Over the next 18 hours, 3 more flares erupted from the same region, C1.8, C3.1, and C4.7, each larger than the last, each occurring roughly 2.1 hours after the previous one, maintaining the cycle that had become 3I/Atlas's signature. By the morning of October 28th, solar physicists worldwide were watching the region. NOAA's Space Weather Prediction Center issued a watch for possible M-class flares, a category 10 times more energetic than C-class. The watch noted unusual localized activity in a region without apparent active region characteristics. The phrasing was diplomatically vague, but everyone monitoring the situation understood. The Sun was responding to 3I/Atlas. Earth's magnetosphere began showing the effects on October 28th at 14 UTC. Ground-based magnetometers detected a sudden compression of the magnetopause, the boundary where Earth's magnetic field meets the solar wind. The compression lasted 47 minutes, during which the magnetopause moved inward by approximately 12,000 kilometers. Satellites in geosynchronous orbit, normally well inside the protective magnetosphere, briefly found themselves exposed to unshielded solar wind. 2 communication satellites reported anomalies. Nothing catastrophic. Brief interruptions in signal processing, the kind of glitch that operators expect during geomagnetic storms. Except there was no geomagnetic storm. The solar wind conditions measured at Earth were elevated, but not extreme. Something else had compressed the magnetosphere. Dr. Vasquez correlated the magnetopause compression with the latest flare from the Sun's corona. The timing matched. The flare had launched a pulse of enhanced solar wind that reached Earth 18 hours later. But the compression was stronger than the solar wind enhancement alone could explain. Vasquez proposed that 3I-ATLAS's magnetic field was amplifying the effect. The comet's magnetic field was channeling solar wind particles along specific pathways, focusing them like a lens. When those focused streams reached Earth, they hit the magnetosphere with concentrated force, creating the compression event satellites had recorded. If this was accurate, the implications were serious. 3I-ATLAS would reach perihelion in less than 24 hours. At closest approach, its magnetic coupling with the Sun would be at maximum strength. Whatever was causing the microflares and focused solar wind streams would intensify, and Earth, positioned on the opposite side of the Sun from the comet, but connected through the Sun's global magnetic field, would feel the effects. NOAA's Space Weather Watch upgraded to a warning. Satellite operators were advised to place systems in safe mode during the perihelion window. Power grid managers received alerts about possible geomagnetically induced currents. Airlines were informed of potential GPS disruptions at high latitudes. You might think this would make headlines. It didn't. The space weather warning was technical, couched in probabilistic language about enhanced conditions and elevated risk. The connection to 3I-ATLAS wasn't mentioned in public advisories. Only those tracking the comet closely understood that a single object, barely 200 meters across, was creating a magnetic bridge between itself and a star 1.5 million kilometers in diameter. And that bridge was starting to conduct energy in both directions. Dr. Marsh's team at ESEP prepared for continuous monitoring during perihelion. All available solar observatories were coordinated. Parker Solar Probe would be at its closest point to the Sun, in perfect position to measure the comet's interaction with the inner corona. Stereo spacecraft would capture the event from side angles. Solar Orbiter would track the magnetic field evolution. Ground-based telescopes would observe from Earth's perspective once 3I-ATLAS emerged from behind the Sun. The data blackout period, when the comet would pass directly behind the solar disk from Earth's view, would last approximately 11 hours. During that window, only spacecraft observations would capture what happened at perihelion. Dr. Takahashi secured observation time on Hinode for the full duration. He told colleagues he expected to see the largest flare sequence yet. What he didn't say, but many were thinking, was that if 3I-ATLAS's acceleration continued to increase right up to perihelion, the object might not survive the encounter.
October 29, 2025, 0623 UTC. 3I/ATLAS reached perihelion. Parker Solar Probe, positioned just 8.5 million kilometers from the Sun's surface, recorded the moment. What the spacecraft's instruments captured would rewrite solar physics textbooks, assuming the data ever became public. The comet's magnetic field, already stronger than any natural expectation, underwent a transformation. In the span of 14 minutes, field strength increased by a factor of 7. The plasma envelope surrounding the nucleus expanded from 400,000 kilometers to nearly 1.2 million kilometers, large enough to engulf 3 Earths side by side. But it wasn't chaotic expansion. The plasma organized itself into a geometric pattern, 12 distinct lobes arranged in perfect symmetry around the nucleus. Dr. Marsh watched the telemetry stream into ESA's control center in real time. The magnetic topology data showed field lines from 3I/ATLAS connecting to the Sun's corona at precise points, not random attachment, but targeted coupling. Each of the 12 plasma lobes linked to a different region of the corona, creating a web of electromagnetic pathways. Energy began flowing, not from the Sun to the comet, as solar heating would suggest, but in both directions.
3I/Atlas was drawing energy from specific coronal structures while simultaneously injecting something back into others. The Sun responded immediately. Within 6 minutes of maximum coupling, solar flares erupted from all 12 connection points simultaneously. Not C-class anymore. 5 M-class flares and 7 smaller events, all triggering at once in a coordinated pattern that defied every model of solar magnetic behavior. The combined energy release equaled a single X-class flare, powerful enough to be considered a major space weather event. But the flares didn't radiate uniformly into space. Their energy channeled back along the magnetic pathways toward 3I/Atlas, creating a feedback loop. Dr. Takahashi's Hinode observations showed the plasma flows in exquisite detail. Material from the solar corona was streaming toward the comet, accelerated to velocities exceeding 800 kilometers per second. The comet's 12 lobes absorbed the incoming plasma, and the object's brightness increased by a factor of 20 in the optical spectrum. For 11 minutes, 3I/Atlas became the second brightest object in the solar system after the Sun itself, visible even in spacecraft coronagraph images that normally block all but the faintest sources. Then, at 0637 UTC, the process reversed. The 12 lobes collapsed inward. The magnetic field strength dropped precipitously. The plasma envelope contracted to less than 100,000 kilometers. In thermal infrared, 3I/Atlas's signature changed completely. The diffuse heat emission vanished, replaced by a concentrated point source radiating at temperatures that suggested the surface had been fused, transformed by the energy exchange with the Sun. When stereo spacecraft captured the first post-perihelion images 3 hours later, the comet looked different. Smaller, denser. The tail, previously a diffuse green stream, now appeared as a tightly collimated beam of plasma, almost laser-like in its coherence. Earth felt the effect 16 hours after perihelion. A geomagnetic storm, classified as G3 on the 5-point scale, erupted without the usual warning signs. No coronal mass ejection had been detected heading toward Earth, yet the magnetosphere convulsed as if struck by a massive solar wind shock. Aurora reached as far south as northern California and Spain. Power grids in Scandinavia reported voltage fluctuations. 63 satellites reported anomalies. The storm lasted 4 hours, then vanished as abruptly as it began. NASA's updated trajectory for 3I/Atlas, posted on October 30th without announcement, showed the object had not only survived perihelion, but emerged on a modified path. The new orbit would keep it in the inner solar system for another 6 months. Whatever 3I/Atlas had done at the Sun, it was far from finished.